Welcome to our final year project presentation, predicting the compressive strength of plastic aggregate concrete using machine learning algorithms. This innovative study is brought to you by our team, Ali Hamza, Mohammed Awais Aslam, and Mohammed Asim Shafiq, under the supervision of Dr. Adnan Nawaz and Mam Sandhira. In today's world, sustainability is no longer optional. Our project integrates artificial intelligence into concrete mix design, especially for concrete containing plastic waste. Since plastic aggregates behave differently from traditional materials, predicting their mechanical properties accurately is crucial. With AI, we aim to reduce dependency on costly and time-consuming physical testing, promoting faster and greener construction methods. The conventional method to evaluate plastic concrete involves extensive lab testing. This process is not only expensive and time-consuming but also impractical on a large scale, especially for power plants or mass production. Hence, the need arises for an automated, accurate prediction system. Our primary objective is to develop a machine learning model that can accurately predict the compressive strength of plastic aggregate concrete, minimizing the need for physical tests while improving efficiency and sustainability. Previous studies have explored the use of regression and meta-analysis techniques to estimate the properties of plastic aggregate concrete. However, they often lacked real-time prediction capabilities and user-friendly interfaces. Our approach builds on this foundation using advanced machine learning models. Our methodology is structured in key phases. First, we train the machine learning algorithm using collected data. Second, we evaluate its performance on test data. Lastly, we prepare the model for deployment through a user-friendly application, making it accessible to engineers and researchers. Our goals were clear: to collect high-quality data, clean and prepare it, train and evaluate machine learning models, and finally, to develop a working prediction interface. We collected a dataset of 164 values sourced from credible research papers. Each data point contains various mix design variables including cement, plastic aggregate, water-cement ratio, coarse and fine aggregates. This SHAP summary plot reveals how each feature impacts the model's prediction. We observe that higher cement content, shown in red on the right, increases strength predictions. In contrast, a higher water-to-cement ratio shifts values left, indicating reduced strength. Plastic aggregate shows a mixed influence, sometimes increasing and sometimes reducing strength, depending on its proportion. The sensitivity analysis quantifies each feature's influence on the model. Cement emerges as the most significant, contributing about 25%, followed by coarse and fine aggregates. Plastic aggregate contributes the least, suggesting that while it affects strength, its impact is less dominant compared to traditional materials. Our heat map reveals strong correlations between variables. Notably, PET percentage is highly correlated with plastic aggregate content. Cement has a strong positive correlation with 28-day strength, while the W/C ratio shows a strong negative correlation, confirming classical concrete theory. Data cleaning was essential. The raw data, shown in orange, contained visible outliers and high variability. After cleaning, shown in green, the data became more compact and consistent, significantly improving features like coarse and fine aggregates. Here, you can visually compare the effect of cleaning. The dataset became smoother, and the outliers were effectively mitigated, leading to better model performance. We trained our model using Google Colab. Initial attempts were not satisfactory. However, with tuning using grid search and switching to an XGBoost regressor, we achieved significant accuracy improvements. This iterative process helped us create a reliable predictive tool. We also developed a simple and accessible user interface. This interface allows engineers to input concrete mix parameters and instantly receive a predicted compressive strength, making it practical for field and research use. To conclude, our project successfully demonstrates how machine learning can aid in sustainable construction by predicting the strength of plastic aggregate concrete. We thank our supervisors and everyone who supported us throughout this journey. Thank you for watching.